La. There we go. I will begin with a word of prayer. Hem. All right, that'll do it. Dear Father, we thank you for this day. Thank you for these students. Just pray that you just guide our steps today. Help us to understand a little bit more about your creation, about gravity, and how that all works. Lord, in your name I pray, Lord Jesus. Amen. So, not yet candidate DeSantis, but now Dr. DeSantis, right? All right. Let's talk about gravity.
Yeah, just forgot.
So, what is the force of gravity exactly? 9.81. Well, how about this? If you've got mass, big M, right, and you've got a little mass out here, little m, then the rule is, if you draw the line that connects these two dudes, right, and that distance is r, all right, then if we talk about the force of gravity due to the large mass m on the little mass m, and I mean, I could do it for, m1 and m2. I think I did that before in here. But the force of gravity, of course, is attractive, so the force of gravity here is what? It's F equals 2 minus g little m times big M divided by r squared times r hat. So r hat is a unit vector in the r direction, all right? So here I've decided to put I decided to put the large mass at the origin. The center of mass of the large mass is at the origin, all right? And this is what Newton's universal law of gravitation says. It says that the force is inversely proportional to the distance between the centers of the masses that are gravitating. And that's it. This is Newton's universal law of gravitation, right? He proposed this, in the sometime in the 17th century, I don't know, 1660, 1670, somewhere in there. What did we think before this? Like, what were the explanations for how did we understand gravity before Newton? I think, what's that? What's that? Kepler. That is true. Kepler does predate Newton by a little bit, right? So when is Kepler around? You guys remember? Is Kepler, I think Copernicus is also back in that time period, right? So Kepler is interesting. Kepler was a sort of a underling of this fellow named Tycho Brahe. Tycho Brahe was a kind of a colorful character. He lost his nose, I think maybe in a duel or something. He had like a metal nose. And what's that? That's dope. Yeah, and the story goes that he died in a drinking contest. Not water. Milk? No, not milk. Because chocolate milk. I have some stories about chocolate milk. I'll tell you those, but not this moment. And so yeah, allegedly the story goes he was a drinking contest. He was so adamant he was going to win, he wouldn't leave the table to use the restroom, and so much so that led to his demise. But yeah, I mean, this is a standard story, all right. So Kepler was working for him, right, for decades. I think at that point he'd been helping Brahe with, observations. He was an astronomer. He had very elaborate and careful observations of the planetary motion. And so, just years and years and years of observations of the planets and so forth, the so-called wandering stars. And so when Tycho Brahe died, Kepler had this giant collection of data to work with. And then, see, Kepler would have liked to show that the planets go in circles, right? But the data said otherwise. The data said that the planets actually go in ellipses, right? So this is what Kepler discovered, not from the basis of that. This came after that, right? Kepler just looked at the data and fit ellipses to the paths of the planets. So that was sitting there waiting to be explained when Newton came along. And in fact, you can derive elliptical orbits from this force equation. If you take, you can solve what's called the two-body problem. The two-body problem is just, you've got, M1 and M2, and you've got what's called a central force that acts on them, in this case gravity. And you can solve that problem. This is the so-called two-body problem. It takes about a good week of a junior level mechanics course to do it properly. It's not a trivial thing, but it can be done. And the solution ends up being for ellipses. Not always ellipses, though. They're either ellipses, parabolas, or hyperbolas, depending on the energy that you have relative to each other, right? So you have orbits which are bound or not. Okay, so obviously the planets are in more or less elliptical orbits, right? You can categorize how elliptical they are in terms of something called the eccentricity, which I'll talk about at the very end of Calculus 2, give or take. Unless I get adventurous and decide to do something more with you guys. But anyway, I guess there was some controversy because in some sense, some people say that Kepler kind of stole the things from Brahe when he died. So maybe those should have gone to his estate or something. I don't know, there's some controversy about this. But all right, so let's get into it. This is the force of gravity then. Oh, you want to know about the chocolate milk?
Yes.
Yeah, so...
Was it Crazy Paul?
No, Crazy Paul does love the Tycho Brahe story. That's one of his favorite stories. He really likes that story. But no, this has nothing to do with Crazy Paul. It has to do with idiots at Red Lobster. Not where you thought this story was going to go, is it? But we once went to Red Lobster, and the kids get kids meals. What comes with kids meal? Free drinks, right? So what do you get when you're a kid and you want a free drink? Chocolate milk. Well, you know where this is going. And you're a server and you bring a child a cup of chocolate milk. What do? They drink it quickly. What do? You bring them another cup of chocolate milk. Have we had dinner yet? No, you're just feeding the child chocolate milk after chocolate milk. What happens to a child if they drink about 2 or 3 cups of chocolate milk fast? What's that? See, you said come back up. You would be correct. I had no pity on that server as they were cleaning up, and it was substantial. So if you ever find yourself doing, if you're a waitress or a waiter as you're trying to make money in college and junk like that, be careful with the chocolate milk, unless you like cleaning up vomit. So, okay, so here we go. Let's see here. Let me set the stage. Let us work on deriving naively. All right. So the naive thing. Here's what makes it naive. Is the sun really just sitting in the center, motionless? Well, no. It's actually, it itself is moving with respect to some other frame of reference. Here's my sun. Use your imagination. Here, I'll make it more. There. Is that more? I don't have a very good sun. I'm sorry. This is just not a good sun at all. I know. I regret everything. There. That's more accurate. There you go. There's your sun. And so we'll make the center of the sun the origin. All right. And then we'll put Earth out here. Obviously, this picture is not to scale, right? So, I mean, first of all, I don't think that even this, my picture of the size of the Earth relative to the size of the sun, of course, is ridiculous, right? The sun is much bigger than that, I think. If I remember right. You guys have seen these pictures, right? So that would be the distance, right? And what happens? The Earth basically orbits around the sun, right? So how does that happen? So let's call this distance r, right? And to a pretty good approximation, though, I said they go in ellipses, right? Well, the orbit of the Earth around the sun it's elliptical, yeah, but it's kind of close to a circle, so it's not too insane. At least as a first approach here, this is all we can do because we don't know how to solve the more complicated elliptical junk. So we'll just basically solve this problem as if the Earth was going in a circle around the sun. So if the Earth is going in a circle around the sun, of course you've got the mass of the sun here, right? And what's the formula then? We've got mass of the Earth, right, times the velocity squared divided by that distance r, whatever it is. So what's making it go in a circle? Gravity, right? Gravity is supplying the centripetal force, right, that's necessary to keep it going in circular motion. So we can equate mv squared over r to the force of gravity, right? And how's that go? Well, you've got big G, mass of the Earth, mass of the sun. What do we got? Divided by r squared, yeah? Now, I guess I should mention to you that this G here is the universal gravitational constant. It is puny. It is 6.67259 times 10 to the minus 11 Newton meters squared per kilogram. It's actually possible to measure this using very, very sneaky things, using like a torsion balance or something. I mean, there's a dude who did it a couple hundred years ago. So this has been known through direct experiment for a while. Not to this degree, right? I mean, some of these are more recent. Okay, but that's the units on this big G are kind of funny, right? A Newton meter squared per kilogram, but that's what you need in order for it to what? In order for it to cancel out the meters squared downstairs, right? And to divide out one of the kilograms upstairs. And did I remember that? I feel like it's wrong. Well, does that make sense? If we does the dimensional analysis work out here? Let's check it for a second here. So we should have the units of G, M over r squared. What should they work out to? Supposedly a what? Should be a Newton, right? So the G is that. What's the units of M and M? Kilograms squared, right? We get divide by meters squared. What you got here? See, I don't believe my notes. Do you? I don't. The meters squareds cancel, and I'm left with a Newton over a Newton kilogram if I don't make an adjustment. I think this is supposed to be kilograms squared. Yeah? Do you guys agree? Someone's consulting Google for me? No? Let me just make sure I'm not talking myself into it. No? Oh, meters cubed kilogram second. Oh, man, well, that's not in terms of newtons. Huh. Well, anyway, let me just, the units on G, they have to be a Newton meters squared over kilograms squared. They have to be. That's what? If we work that out, that's a kilogram meter times meters squared over seconds squared, kilograms squared. What's that? So we get meters cubed over seconds squared kilogram, I think. So cubic in meters, dividing by seconds squared, dividing by mass. That should be the units of G. I think that's what I just saw here when I searched it. Meters cubed, 1 over kilograms, 1 over seconds squared. Yeah, that's it. So my notes have an unhelpful error. My notes are missing. So I'm in lecture 31. There's a typo on my on page 1. So that's supposed to be Newton meters squared over kilograms squared. There's a 2 missing there. Okay, now that I got that out of my system, how do we solve this problem? I mean, that's it, right? That's the relation between the velocity of the orbit, right? The radius of the orbit, mass of the Earth, mass of the Sun. Now, what is the first thing you notice? The mass of the Earth does what? Cancels, right? And then you've got v squared, and this would give me r, v squared r, right, is equal to g times the mass of the Sun. Now, how does the velocity relate to the radius, guys? How far do you go? Let's let big T equal the period of orbit. So we know that for the Earth, right? That's 1 year, right? For the Earth. You guys are not flat earthers, right? You believe in like orbital mechanics and such, no? Okay, just checking. Okay, so if that's the period of the orbit, how far does the orbit go? How far is it? 2 pi r, right? So what's that make the speed if it's constant? We've got 2 pi r divided by the orbital period, which is t. So you square that. You multiply by r, you got GMS over here. What's this give us? This gives us r cubed is equal to g, mass of the Sun, divided by 4 pi squared times t squared. So this right here, guys, this is called Kepler's law. So this is basically what Kepler discovered as I was describing. Now, I'm lying because Kepler's law actually is for ellipses, right? But this is the relation, this is what Kepler found for like the semi-major axis relative to the period of the orbit. So it's still true, it's just with the, you have to, in terms of elliptical math, not circular math, all right? So what's really interesting about this, right, is that this constant here, it's independent of the Earth, right? So if we can derive this for the Earth, we could just as well do it for Mars, right? And so like we have this rule that the cube of the radius for the Earth, right, divided by, the period for the Earth, also known as a year, squared. Well, that's equal to, what is it equal to? It's equal to g times the mass of the Sun divided by 4 pi squared, right? But that's also equal to lots of other stuff, like the radius of the orbit of Mars cubed, divided by the period for Mars. How long is a Martian year? I have no earthly idea, right? Anybody happen to know? Yeah.
It might be 2 years.
2 years? Did you notice something here? We can calculate the mass of the Sun if we know the what? The radius of the Earth's orbit and how long it takes, right? Let's see here. So, yeah, you're just about right, 687 Earth days. So, let's see, what is that? 687. Yeah, you're really close. 1.88. So, the period for Mars 1.88 years, right? By the way, what is this? This has a name. This is equal to 1 astronomical unit. An astronomical unit is the average orbital radius of the Earth from the Sun. So a lot of times the friendly way to ask these questions is, what's the radius of Mars in astronomical units? Okay, we could do that here. So I guess this is example 2. This was example 1, if you want me to number them. So how do we figure, if we know this, and you can beg the question, how on earth do you know that, right? But that would be from, you can kind of observe, I don't know, it's a complicated question for astronomers, right? But somehow we have learned, okay, honestly, through Google, but that the period from, the Martian year is 1.88 Earth years. And let us agree to have a convention in here that when we speak of years, we always mean years in terms of Earth years, okay? That has always been assumed up to this point, but now it matters. Okay, so then what is the, we got what? R for Mars should be the cube root, right, of our Earth cubed times the square of the Martian year divided by the square of the Earth year, right? And so what is that? That's just the cube root of 1.88 squared divided by 1 squared times the radius, the radius of the Earth orbit. Obviously, I'm not talking about the radius of the Earth or Mars as a planet. That's a different discussion, right? We can talk about that next. In fact, let's talk about that. But what does this work out to? So the radius of Mars orbit is roughly what? This is not a calculator. What am I doing? What did you guys tell me? 1.52. 1.52? Is that right? Is Mars further out? I guess it is, right? So Mars is further from the sun than the Earth. See, this is what I am not an astronomy buff, right? Like, for shame to even ask, to even make this comment, right? Which is the one's closer to the sun? It's called what? Venus or what? Yeah, Mercury. I was thinking Mercury, but yeah. So there you go. So we could figure out the mass of the sun from some of this data. How would we do it? What's the mass of the sun equal to? Let's work it out. What's the mass of the sun? Well, notice that we have this formula right here, right? We can solve the Kepler's law for the mass of the sun. What's it equal to? Now we're going to need to look up something here in a second, but the mass of the sun should be equal to 4 pi squared, the radius of the Earth's orbit around the sun cubed, divided by what? G times the t squared, right? Okay, so what are these numbers? Well, I know what 4 and pi are, so I got that. The distance from the Earth to the sun is what? It's like about 8 or 9 light minutes, right? You've heard this, yes? What's that? We just put astronomical unit, but I want to work it out. So like just putting 1 astronomical unit there is, I mean, yes, we could write the mass of the sun in terms of astronomical units, but that would not help our larger purposes, would it? So mass of the sun, oh, wait a minute, I don't want to do that. Astronomical unit, what is it exactly? Astronomical unit is defined to be 149.6 million kilometers. 149.6 million kilometers. Let's write that in a more civilized way. That is 1.496 times 10 to the what meters?
11.
This is 6. This is 3. 11, yeah. I think that's right. So, yeah, because that's a 10 to the 3, that's a 10 to the 6, that's a 9. I moved it to 11, yeah. Okay, so, whoa, yowzers. So 1.4, that's kind of big, isn't it? 1.496 times 10 to the 11 meters. We got to cube that thing. What was my G? 6.6, what was it, 7? I can't remember. I used to know this. 6.672, well, probably 6.67 is enough. Times 10 to the what? Minus 11? And let's see here, I was just quibbling over this a second ago. What were the units on this thing? Can you help me out? Meters cubed over second squared kilogram. There's my G. My time is, we're gonna ignore the leap year thing. We're just gonna do 365. That's the number of days. How many hours are there? How many seconds are there in a day? The answer is 86,400. Woohoo! So there you go. That's the number of seconds in a year. I gotta square that thing. Am I wrong?
No.
Oh, was it?
And on these sorts of problems, if they appear on a test, are we expected to memorize or write down the gravitational constant, or will that be provided for us?
You should know the gravitational constant. I think you have a 3x5 card, so it should find its way on there, yeah. In case I forget to put it. It is in this calculator for what it's worth. If you have one of these deals, it's in the back. It's under like 39. So if you do constant 39, it's right here. If you have a Texas Instruments, well, you wasted your money. What can I tell you? Sorry. If you forgot to write it on the card, just ask me. I would tell you. So, yeah. So crunch the numbers. What do you get? Justin, did you do it? 1.99 times 10 to the 30th. Now, you actually did these numbers and it works out to that?
Yeah.
Cool, because that is the actual mass of the sun, 30th kilograms. So there you go. The mass of the sun is about 2 times 10 to the 30th kilograms. See, so we can apply the same logic to like the Earth-Moon system, right? The gravitational pull on the moon is primarily from the Earth, right? So you can also estimate the mass of the Earth from that if you wanted. Yeah? What's it? Oh, okay. Any questions? So, hypothetical. Let's see here. So if we think about the Earth, right? Its radius, let's say, is r. What is the force of gravity on a person? How does it relate to this? So the force of gravity right at the surface of the Earth is what? It's G, mass of the dude, mass of the Earth, right? Divided by r squared. And that's equal to what? Well, there's no mv squared over r stuff going on here. This is just equal to mg, right? By our definition. So this is the gravitational acceleration on the surface of the Earth is characteristic of the radius of the Earth, the mass of the Earth, right? Like that. So you can work this out. And let's see here. So what do we get? G is equal to what? Big G, mass of the Earth, divided by the radius of the Earth squared. So what's that? Well, I'd have to look up these numbers, right? But if I do, and I will, see the mass of the Earth, do you guys know? So 5.97 times 10 to the 24th. (10 to the 24th), and let's see, what's the radius for the Earth. I mean, the Earth is technically not a sphere, right? The Earth is actually a, what is it? An oblate spheroid, that's right. But to a good, what? Was it funny that he said it right?
What's it called?
An oblate spheroid?
Okay.
Do I need to, it's a squished sphere. The reason it's squished is because the Earth's spinning, right? So the centripetal force or the acceleration at the equator makes it bulge out a little bit. Whereas you don't have that centripetal force at the poles, so it doesn't. In fact, the acceleration due to gravity is about, well, the net acceleration at the circumference is about like 0.1 less because of this. All right, so radius of the Earth is about 6,378 kilometers. Let's write that more civilized. Let's say 6.378 times 10 to the 6th meters. What'd I just say? 10 to the, you know, that really hurts. 10 to the 6th meters. So the radius of the Earth is about 6.4 million meters, right? Let's see here. I think kilometers is a little bit more useful. How many miles is that? Yeah, 6,400. What do we got? 6,400 kilometers. How many kilometers in a mile? About 1.6, right? So we're talking about just under 4,000 miles. That's the radius of the Earth, about 4,000 miles. So whenever you hear somebody bragging about drilling to the center of the Earth and they were like, we're like 10 miles down, go, shut up. The radius of the Earth is 4,000 miles. Your 10 miles is nothing, right? Even if you were to drill 100 miles down, that'd still be pretty much nothing, right? What's the deepest we've ever drilled? 2 miles. Is that right? I have no idea. I've learned that whenever I see some link to something about some sort of like deep drilling something or other, it's always an ad for some stupid thing that never gets to anything. So I refuse to click on it. But anyway, so what we got here is my G, 6.67 times 10 to the minus 11, right? Mass of the Earth, 5.97 times 10 to the 24, divided by 6.378 times 10 to the 6th. Square that thing. The units are going to work out to meters per second squared, right? Because I put everything in terms of meters, seconds, and kilograms. And what's that work out to? Well, I think we know what this works out to, right? But my point to you is that Newton's universal law of gravitation is giving us an explanation for why G is what it is, right? So that's interesting. See me run the numbers here. I get like 9.79, roughly speaking, times 9.79 meters per second squared, right? So you can ask fun, like once you have this, right? We could ask other questions like, what would the force of what would the acceleration due to gravity be if hypothetically the radius of the Earth was what? A half what it is. How strong would gravity be in that hypothetical world, right? You guys understand my question? What's the force of gravity on the surface of an Earth which has been compressed to half its radius? You said it's 4 times it? I think you're right. Let me write that out. You know, supposing same mass, what is G on, let me say, I need to come up with a different, G, for us, G means 9.8 meters per second squared, right? It's a fixed, we have a fixed meaning for G in this course, so I need to be, you know, making G a variable is kind of like making 7 a variable. You shouldn't do it. So let's say G, I need to come up with a name. Bob. There we go. What is G Bob given the radius for Bob? Did I use big R? I used big R, didn't I? All right, so the radius for big Bob here is equal to the radius of the Earth divided by 2. So we know that if we solve for G Bob, what do we get? Let me actually run through the logic here rather than just telling you the answer. So the logic is this: the mass times the Bob gravitation, whatever it is, we don't know it. It's going to be G times mass of the Earth, right? Same mass, divided by what? The radius of Bob squared. So where is this coming from? This is just Newton's universal law of gravitation applied to the mass at the surface, right? And this is really the definition of G sub Bob, right? This is what we mean by gravitational acceleration at the surface of a planet, all right? Now, so this is G mass of the Earth. Now, yeah, there's 2 different ways to do this problem, right? The one way, and it's very tempting on your homework if you have a problem like this, which is to what? Well, you know the numbers, right? You got the big G, you got the mass of the Earth, you got the radius of the Earth. Yes, sir.
Don't you need a small m on the side of the...
Oh, yeah. Thank you. Thank you very much. So you know all these masses, right? So it's very, I've seen students do this. They like put all the numbers in to work it out, but it's much wiser to be symbolic here and not resist the temptation to put the numbers in. We could, right? You could be like, well, Bob's radius is, whatever half of 6.378 is, Okay, but anyway, here we go. So you do that, and that gives you 4. Let me just get to this G Bob divided by the little m that you guys reminded me to put there. Good. So we've got 4 times G times the mass of the Earth divided by the radius of the Earth squared, right? But we already know that this is G, right? So what you guys told me a few minutes ago is correct. If we half the radius, we end up we don't just double the gravity, right? It quadruples it. Gravity's nonlinear, all right? Conversely, what happens if you go from the radius of the Earth, right, and go out to twice the radius of the Earth? What's gravity out there? It's not G over 2, right? It's what? It's G over 4, right? So this is how gravitation is. It's inverse square. Let's see here. Okay, so yeah, I think it's, the story of Kepler is interesting, right? Because there was a lot of philosophy at the time that said that the motion should be circular, right? Because circles were perfect. And so this was so much so that around that time, astronomers would try to fit the motion of planets into circles and then circles on top of circles. Do you guys know what these are called? What is it if you have circles upon circles upon circles? A cylinder? No. These are called epicycles. So if you start trying to break motions into like composite of multiple circular motions, you can do all kinds of like interesting, crazy stuff. I can show you if you want to see it. It'll take me a minute. But actually, you can actually create almost arbitrary paths using circles. Let's see here. Come on, you can do it. Well, that's not that exciting. Let's see here. Let me make this a little bit more. There we go. I'll add a 10 to that. That'll make it more energetic. Come on, get in there. So this, what you're looking at, and it's not cooperating with me at the moment. There. So this weirdo curve we're looking at, right? Does this look like a circle? I mean, it doesn't, does it? But what this is, honestly, is just two circles added together. Adding two circles together, you can generate this curve. I did it in 2 minutes. If you have 3 circles, you can generate more complicated curves with more efficiency, right? And so the astronomers of the time of Kepler, they were doing this kind of stuff for the planets. So they'd have the planet going on a circle, and then it's on top of another circle. And so if you have a circle on a circle, you can make the planet kind of... And they worked. I mean, epicycles worked. Like, you could actually generate the motion of the planets using circles upon circles. Right? Because actually using circles upon circles allows you to generate pretty much arbitrary curves. It's an incredibly flexible template on which to draw things. So it was quite an achievement of Kepler to realize that these, ellipses get the motion of the planet. You didn't need to use circles on circles, you could just use a single ellipse, all right? But Kepler had no explanation for where the ellipse came from. He was just fitting data. Then about, I forget the exact history here, but maybe about 100 years later or so, Newton came along, proposed the universal law of gravitation, and then solved Newton's equation, as we call it, and showed that ellipses are solutions to the universal law of gravitation. All right? So it's very, and it's interesting, right? Because one of the interesting aspects of this is Newton was proposing that the same physics, right, the same physics which governs astronomical motion is the same physics that, governs this, right? Like the same gravity that does this moves this, moves the planets around and so forth. And the ancients had the habit of, giving different explanations for different physics. Like, there's one kind of physics for moving rocks around on the Earth, right? There's a different kind of physics for the way that the motion of the stars and so forth. So it was a synthesis to talk about both in terms of the same overarching law. Although there is a failing of Newtonian gravity, right? So, like, what happens when the radius changes? The force would change, right? What are the dynamics of that? How exactly does the force change over time? Newton's theory of gravity doesn't have any answer for this. There's no well-accepted understanding of what we'd call gravity waves, how gravity is propagated. Like Newton's laws pretty much just apply to static situations where things are already where they are in some sense. Okay, there's two different things. It can explain if the gravitational field is set up by the large gravitating body, all right? That's not changing. That's essentially static in time. Things move through that, okay? We can solve that. But to explain that large gravitational field changing, right? That's what Newton's universal law of gravitation has no answer for. He was aware of this. He said it was spooky action at a distance. It doesn't explain how does the force of gravity get from mass 1 to mass 2? How does the force of gravity get from the Earth to the Sun? Newton's law of gravity has no explanation for this whatsoever, no mechanism. It was hundreds of years later. This is what Einstein's general relativity did. Is it gave a mechanism, a possible explanation for how gravity propagates then through space-time, through what are called gravitational waves, which we observed for the first time maybe 10 years ago through something called LIGO, which I think it was LIGO that got it. It's a light it's these large laser-based interferometry. They look for interference of light waves, basically. And you can pick up on the gravity ripples. It's very subtle. It takes an incredible event for it to actually be observable. Something like a black hole sucking in a neutron star, or something stupid like that. But anyway, even so, general relativity is not a single theory. Actually, it could be understood to be a family of theories, because we only have a few. The experimental tests we have of general relativity are mostly in the weak field region, and there could be different kinds of theories that would have the stronger field where we have less data. We don't really know for sure which theory is the correct one. We just don't have enough data. So general relativity even is not really a specific theory. It is in some sense a family of theories, if you understand it. So the next example I usually do in here, and I'll probably do it next time because I don't want to rush it today. But do you guys know about what's called geosynchronous orbit? Anybody know what that is? So
Is that like a satellite? Like when you look up and it's all
yeah, you look up and the satellite's always in the same spot. That's exactly it. What does that mean about the satellite? Yeah.
It has the same orbital speed as the Earth.
Right. And what is the orbital speed of the Earth?
1 astronomical unit.
1 astronomical unit would be incorrect. So, I mean, it is an astronomical unit we're talking about, I suppose. But if we drew a picture of the Earth like this, and it's got a rotational speed around its axis, right? Earth. What's the omega here? 1 per day? That would be correct. Revolution per day. Can we put this in more useful and common? Like, what's a revolution? 2 pi radians, right? So 2 pi radians, how much is a day? 86,400 seconds. So what's the angular velocity of the Earth? Whoa, 7.27 times 10 to the minus fifth radians per second. So one of the common refrains of the flat Earth crowd is, you say the Earth is spinning, I don't feel anything. Yes, that's right, because the Earth is spinning very slowly in terms of radians per second, right? And you're like, well, but it's still a fast speed. That is true. The speed is relatively speaking fast. How fast is it? Omega r, right? So how fast is the Earth spinning? If we do the equator, I had the number up here. What was it? What was the radius of the Earth? What was it? Radius of the Earth was what? 6.38 times 10 to the what? 6th, was it? So what's that speed? If I didn't remember it wrong. So if I didn't do it wrong, 463 point, well, let's just say 464. Roughly speaking, 464 meters per second. Now the flat earthers would be like, see, I told you we're moving. You'd feel that. Context, right? What is the centripetal acceleration that comes from that? AC is what? V squared over r, right? But what does that look like in terms of omega? That's omega squared r, right? So anyway, if you work this out, it's about like 0.1, and that's the biggest it can be at the the equatorial circumference there. So that's why we don't feel the Earth rotating. It's because it's too small. If the Earth was spinning 100 times faster, we'd all be holding on for dear life, right? I mean, it'd be different, but it's not. Anyway, I'm going over time. I'm sorry, but hey, I went under time the other day, so I'm making up for it. Don't say I didn't cheat you out of class time.